In this video, we're going to talk about derivatives of exponential and logarithmic functions. And our first rule is going to be that the derivative of any exponential function, b to the x, is equivalent to ln of b times b to the x. And this only works if b is larger than 0. That's the same exact rule for our logarithms too, and we used to do that. So let's take a look at a couple examples and see exactly how to use this. So our first example is going to be f of x equals 4 to the 3x. So what we have to understand first is that this exponent right here is not just x, it's a 3x, which implies the chain rule. So we first of all have to break this up into our composite functions. So our outside function is f of x, our inside function is g, and then we'll take the derivatives of each of those respectfully. So in this case, we are going to have an outside function of 4 to the x, and what do I plug into x to make that work? I plug in 3x. So there's my two composite functions, and then we're going to take the derivatives of each of them individually. So f prime will imply our new rule, and b right here is the base of our exponential function. So this is going to turn out to be the ln of 4, just like so, times 4 to the x. So that's the first part that we have. G prime is just going to be 3. So we have to put this together is our chain rule, which if you recall is f prime of g times g prime. So let's go ahead and put this together. F prime of g, so I'm going to take my g function and plug it in to my x in f prime. So that's going to look like ln of 4 times 4 to the 3x, and then I have to multiply this by g prime, which is 3. So to clean this up just a tiny little bit, we can actually go ahead and multiply this ln of 4 by the 3, and it would look something like this. 3 ln of 4. And of course this needs to stay inside parentheses, and this is times 4 to the 3x. So that's how we use this new rule. Let's take a look at another one. This one's going to be f of x equals 5 to the x squared. And of course this is still a chain rule because our exponent is not just a plain old x. So let's break this down into our composites. So f and f prime, and then g and g prime. So our outside function is 5 to the x, and we're going to plug in x squared into it. So our f prime is going to use our new rule because our x is in the exponent. So this is going to be ln of 5 times 5 to the x. And our g prime is 2x. So we're going to carefully put together our chain rule. So it's f prime of g, so here's my g. I plug it into this x. So that's going to be ln of 5 times 5 to the x squared, and then we multiply all this by g prime, which is 2x. And again, we can go ahead and multiply these two together, or at least put the 2x up front, just to clean it up a little bit. So this could be 2x ln of 5 times 5 to the x squared. So there we go. Okay, so we're going to move ahead to our next rule, which is the derivative of a natural logarithm, which is simply equivalent to 1 over x, whatever x may be. And again, this can only work if x is greater than 0. So let's take a look at a couple examples. Here's our first one, y equals x times ln x. And this is actually a product rule built in with our logarithmic derivative. So product rule, if you recall, is f times g prime plus g times f prime. So we can go ahead and do that. Our f is going to be x, and our g is going to be ln x. If it helps, please break these down first. So for example, I would do f and f prime, just like I've been doing, and I would do g and g prime. So f is going to be my first part, which is x, whose derivative is just 1. G is going to be ln x, whose derivative is simply 1 over x. So we're going to put all of this together, and I'm going to get x times g prime, which is 1 over x, plus g, which is ln x, times f prime, which is 1. So we want to notice here in the first part that these x's are going to cancel, and all I'm going to be left with is a 1, and ln x times 1 is just ln x. So this would be my final answer. Let's take a look at one more of these kind. This one's going to be ln x cubed. This is, again, a composite function, so this is going to require a chain rule. So let's go ahead and break it down into f prime, g and g prime. Our outside function is going to be x cubed, and we are going to plug in ln x into it to get my original function back. And now we take the derivative individually. So the derivative of x cubed is 3x squared. The derivative of ln x is 1 over x. And now we're going to follow our chain rule. So I'm going to plug in g into my f prime function. So that's going to be 3 times ln x squared, and then times g prime, which is 1 over x. And to clean this up, I'm going to take this piece and multiply it by 3. And that's just going to give me 3 over x. And all this is times ln x squared. So that's all there is to that. Our next rule is if we're taking the ln of something besides just a plain old x. This is if we've got 2x in here, or x squared, something like that. And we can still see the 1 over x part. If this f of x was my x, it still goes into the denominator. The only difference between this rule and the one before is that this time I take the derivative of that inside part and put it as my numerator. So it's kind of like a built-in chain rule for us, which is actually really helpful. Let's take a look at an example. So we're going to do y equals the ln of x cubed plus 1. So just by following our rule, this is going to be our ln part, and then this is our f of x. And again, if you find it helpful, find the derivative of that inside part first. So the derivative of that inside piece is just 3x squared. So to put this all together, I get my fraction bar set up. That inside part goes all together in the denominator, and then our numerator is the derivative, which is 3x squared. And nothing here actually cancels or simplifies, so this is my final answer. Let's take a look at another one. So this time we're going to have y equals the ln of the square root of sine x. And whenever we see square roots, we do want to get in the habit of rewriting them as an exponent to the 1/2 power. So this is the ln of sine x to the 1/2 power. Now, if you don't remember your logarithm rules, you're going to have to do the chain rule twice, because this is going to be a problem. However, we know that we have a power property for logarithms, and that the exponent becomes the coefficient. So this is 1/2 ln of sine x. So that made that situation way easier. So we're going to go ahead and find our f of x, which is this part right here, and we're going to find its derivative. So f prime of x, the derivative of sine is simply cosine, and the 1/2 is just going to follow along. So what we're going to do all together is I'm going to bring down my 1/2, and then I'm going to multiply it by the fraction that I'm supposed to get for my ln of a function. So the denominator is the original inside part, which in this case is sine x, and then the numerator is filled in with my derivative of that part, which is cosine x. Now we know that cosine x over sine x is equivalent to cotangent, so this is all going to become 1/2 cotangent x, and that's it. Our next rule is going to be d dx of log base a of x is equivalent to 1 over x times the ln of a. So we see both the base here and the argument here. So we just have to remember their placement. So let's take a look at an example that goes with this. So we're going to use a really straightforward example. We're going to find d dx of log base 10 of x. And we all know that base 10 is our base for our common logarithms. So this is a pretty straightforward problem. We need to first of all identify our base and our argument. So we're going to have our fraction bar all set up. 1 goes in the numerator. Our x in this case is still just x. And we would take the natural logarithm of the base, which is 10. And that is seriously all there is to that. I'm going to work out one very complicated problem for us so that we can see this logarithms in their full beauty. This last problem is pretty complex and it requires a lot of our older logarithm rules. Alright, so here we go. We're going to calculate the derivative of this. Now, the reason why this plays a part in logarithms, because I don't see any here, is because I can actually separate these up into logarithms. Please recall that if you just look in the numerator for me, this right here, this product of these binomials, okay, in logarithms, products become addition of logarithms. And this right here, division, becomes subtraction of logarithms. So I'm going to rewrite this entire thing only with natural logs. So I work with the numerator first. I'm going to rewrite that multiplication as the addition of two different logarithms. So that becomes the ln of x plus 1 squared, that's the first part, plus the natural logarithm of 2x squared minus 3, and now the division becomes subtraction, minus ln, and I'm going to rewrite this right now because I see square root, and that should be an exponent to the 1/2 power. So x squared plus 1 to the 1/2 power. So now what we're going to do is take the derivative of each of these individually. So for the first part, I'm going to take care of my exponent first. This can come down in front, and this becomes 2, and then I'm going to take the derivative of the ln of x plus 1. So the x plus 1 goes in the denominator. The derivative of that denominator is just 1. So that's the first part. The next part, I do not see any exponents that can be brought to the front, so we're just going to go right ahead into the derivative part. So 2x squared minus 3 is my denominator. The derivative of that is just 4x. So that's that. The last part, I do see another power that I can bring down in front. Please don't forget that your negative sign needs to stay there. So this is going to be minus 1/2 times our fraction bar, and x squared plus 1 goes in our denominator. The derivative of that is 2x. So now we have a lot of cleaning up to do. So this becomes 2 over x plus 1 plus 4x over 2x squared minus 3 minus, oops, that's not a 1. 1 times 2x is 2x, and then 2 times the denominator is 2x squared plus 2. And this would be our final answer if in the very, very beginning we had f of x equals the natural log of all this. However, that's not the case. We took the ln of that side, which means we had to have also done it to this side as well. So there's one very simple way to take care of that. This right here is the ln of f of x. This is our rule that we've been working with, right? And the ln of f of x is where you take the fraction and you put your original in the denominator and the derivative of that in the numerator. So a simple way to think about this is f of x was y. So if I take the ln of y, right, that becomes y in the denominator and y prime in the numerator. Well, I just want y prime to be equal to all of this beauty that I got here. But I can't do that yet because I've got this denominator to worry about. And the only way to get rid of him is to multiply both sides by that denominator, which in this case is the original disgusting function. So the way that we're going to do this is I'm going to get rid of these curly brackets, and we are just going to put a nice big pair of parentheses or brackets around this, and then out at the end we are going to multiply this by the original function. And since I have like no room here, I'm actually not even going to do that fraction bar. I'm just going to say that we multiply it by f of x, or by that y. So when you start off with a fraction like this and you don't already have the natural logarithm in there, then please make sure that at the very, very end you do this one last step where you multiply both sides by that original function, because you had to have taken the natural logarithm of the left-hand side as well. All right, that's it. That's going to conclude this tutorial.